Right, so this is question 2. We're using a signal generator and an oscilloscope. We need to know how the settings on an oscilloscope work and what we get out of it. So if we have a look at these traces, figure 7 and figure 8, so this is the ground line trace, which is the same here. So that is at 0 volts there. So that must be the same. So that's at 0 volts there. Now if we look at our volts per division, here we've got 1 volt per division. The easiest way to do these is to draw onto the oscilloscope trace your values. So 1, 2, 3, 4, 5, 6 and 7. So first of all we need to determine the peak-to-peak voltage of V. So we want the difference between there and there. So if that's 0, that's 6.3. So it's 6.3 volts just being read off there. Then we need to determine the frequency here. So we start there. We want to get to the same place, so we need to get to there. So we go 1 box, 2 divisions, 3 divisions, 4 divisions, 5 divisions, 6 divisions, 7 divisions, 8 divisions. So that's 8 divisions at, what's their value? 0.5 milliseconds each is 4 milliseconds. Then you have F is equal to 1 over T, so that's T is equal to 4 milliseconds. The time it takes to complete 1 full cycle, which is equal to 1 over 4 times 10 to the minus 3, to 250 Hertz. Okay, so I've just copied the values from the earlier in the question down here, the 2 different scales. So we've got this capacitor charging and discharging circuit. Right, so you need to know what's going on with capacitors here, as well as being able to determine the experimental stuff and extract information from these. So what's happening is every time when you close this, every time the signal goes onto a high section, then it's going to drive current through here, through this resistor, onto the top of the capacitor, charging the capacitor up. So there it goes, charging the capacitor up. And every time you take it low again, like so, then this point is going to be at a higher voltage than this point, which means that current's going to flow backwards through that resistor, that way, into the signal generator, which is going to remove charge from the top of the capacitor, which is going to discharge the capacitor. So the voltage across the capacitor will drop like this, and it will drop back down pretty much to 0, and waiting till the signal generator increases the potential here again, when it'll charge up. So it's constantly charging and discharging. Right, you could do the exact same thing with a switch. If we had a cell like so, a switch like this, a resistor and a capacitor here, and we had another switch like this, you've probably seen a circuit a little bit like this. You throw the switch to this side, the capacitor will charge up through this resistor. You throw the switch to the other side, the capacitor will discharge through that resistor, through the same resistor. So all that's happening is your signal generator is effectively being this switch, flicking it back between the charging cycle and the discharging cycle, backwards and forwards continuously. So that's essentially what it's doing, but it's doing it 200 times every second. Okay, so determine the time constant of this. Right, so we need to learn a little, well, we need to know a little bit about our capacitors to do this, and the time it takes to discharge / charge, no, we'll just do discharge. The time it takes to discharge to 1 over E of the original value is RC seconds. And that's what we're trying to find, the time constant. You should know that off by heart. If you don't, then it doesn't matter. You can use the equation here. You can use V is equal to V naught e to the minus t over RC. For the discharge one, you just put in here any value you like, a big value, half or more, and you'll find that you'll get out the time it takes to discharge to that value. You can read them off the graph, but I'm not going to use that. I'm going to use this. If you just put if you put V there as 1 over E, you'll find that T is equal to RC exactly. I could show you that, so hang on. So we've got V is over E is equal to V naught. So V naught over E is the new value, V naught is the original value, e to the minus t over RC. So we cancel those and we get 1 over E there. We take logs of this and we have ln of 1 over E is equal to minus t over RC. Well, the ln of 1 over E is minus 1 is equal to minus t over RC, so t is equal to RC. So that's the proof there. But the thing that you should probably just know is that in the time constant, it discharges to 1 over E of its original value. So we've got 6.3 volts divided by E is equal to 6.3 divided by e to the power 1 is equal to 2.32 volts. Right, so we need to find 2.23 volts. So it starts here on the discharging, and we need to get 2.32. So that's 1, that's 2, that's 2.2, that's 2.3. So we're trying to get to there. Which means we're basically there, aren't we? It's quite difficult to do this accurately. They get a bit of leeway on this. So that is 0.6 divisions. So that takes 0.6 divisions, and each division is 0.5 milliseconds. So 0.5 times by 0.6 is equal to 0.3 milliseconds, which is equal to 0.3 times 10 to the minus 3 seconds. Right. So you need to know a bit about capacitors, but once you know a bit about capacitors, you can just read it off the graph. Or you could take 2 points. So you could take this point, for instance, and this point here, work out what the time is from here to here, work out what the two potentials are, and then just use this equation here in order to work it out. Students suggest testing the time base to 0.2 milliseconds per division might reduce the uncertainty in the determination of the time constant. State and explain any possible advantage or disadvantage of making this suggested adjustment. So I think we need to talk about the advantage here. I can't really see any disadvantages to doing this. This would make a lot of sense. So what we're going to do is we're going to, if we change this from 0.5 to 0.2, we're going to stretch the wave out that way. So it's going to look all stretched out, which means that the same drop there is going to take more boxes, which means it's going to be easier to measure, so therefore reducing the percentage uncertainty. So we've got to explain that. So state and explain a possible advantage. This would stretch the wave out. Right, now they've given values, look, so they've given 0.2 milliseconds per division. So we can be specific by exactly how much it's going to stretch it out. It's going to stretch it out by 2.5 times, because that is 2.5 times bigger than that. By 2.5 times horizontally. This will make it easier to read and reduce the percentage uncertainty in the measurement of time. Now, my first time through, I didn't actually put this bit in, but I realised I really should have, because they are specific in the time. It doesn't just say the student suggests lowering the time base. It actually says setting a value to a specific value. And because it's set to a specific value, we should be specific about how the wave is stretched out. So I'm just going to sketch it now. It goes to this. Okay, so whereas before we were measuring that distance there, now we're measuring that distance there. Okay, so that was RC before, this is RC now. So that's at 0.5 millisecond per division, that's at 0.2 millisecond per division. Okay. Looks like that stopped, doesn't it? Right, I think that clears that one up. Right, this question here. A student connects an identical resistor in parallel with R. So another resistor is put there of identical value. What happens is the question. Well, what's the new value of R? That's the first thing to say. So the value of resistance will halve, because you've got two resistors in parallel, they are identical, so you just divide by the number of resistors there are, so that's R divided by 2. So our new value of R will be our original value of R divided by 2. Therefore, the time constant will halve. Therefore, it takes half as long to charge and discharge. Okay, so what we need to do now is to draw on this the new shape. So this is going to be exactly the same, but its discharge is going to discharge in half the time. So there it's pretty much fully discharged, which is that point there. It started discharging there, so we want halfway between there for its new discharge time, so that's going to be there. So it's going to fully discharge by there. This point here, for instance, will move halfway back towards the back towards the point where it started to discharge there. So it'll move back to that one there. So we need to, first line we need to draw through that point there and that point there. So this is a little bit tricky, but not too bad. And we need it to hit the exact same discharge point there. So there it goes. And then it's going to look the exact same going up. So this point here needs to move towards this point here, halfway. Halfway is there. And this point here needs to move towards this point here, about halfway, which is there. So good, that one. There we go. And then this one will once again discharge quicker, almost have discharged all the way by the time it gets to there. It's rounded. Again, make sure that's rounded off as well. So it's just discharging in a shorter amount of time, but it's actually discharging exactly half the amount of time. So you can halve the distance from where it started to wherever it is that you got to. You can just halve the distance. So That's where it started, that's where it's got to, so halfway between there and there is about there. So it looks a bit like that. Right, this part here, 2 part 6, here we have the original trace from the signal generator. This one shows what happens when you put it through this circuit here. Now you swap the position of the capacitor and the resistor around, and what do you see here? Okay. So we got the signal generator. Then we have the capacitor and the resistor. And we are still measuring the potential difference across the resistor here. Right. This is a little bit more tricky to explain. Once this has been running for a length of time, once a set value has been on here, a constant value has been on here, then any potential difference between here and here will have driven a current one way or the other to either charge or discharge the capacitor to make the potential difference across this resistor equal to 0. You'll see why that is a bit later more clearly. So it starts at 0 along here. Right. Now, the potential difference here suddenly drops by about, let's say, 6 volts. So if the potential difference at this side of the capacitor suddenly drops by 6 volts, the capacitor cannot charge or discharge instantly. So, if the signal generator's potential suddenly drops by 6 volts, what happens? Well, there's a voltage drop across the capacitor, which is something. We can work out what it is. Initially, if the voltage across the resistor is 0 volts, the voltage across the capacitor will be all the rest. So it will be this, it will be V. So the voltage across the capacitor starts at 6 volts. Here. Now, when this drops by 6 volts here, the voltage across the capacitor cannot change. It can't charge or discharge instantly. So therefore, the voltage across the capacitor still has to be 6 volts. So if this side of the capacitor drops from 6 volts down to 0 volts, this side goes from 6 volts down to 0 volts. This side, started at 0 volts, must also drop by the exact same amount down to minus 6 volts. And the reason this got to drop to minus 6 volts is because the potential difference across this capacitor has to remain the same. It can't charge or discharge instantly. As this jumps down, this thing can't change that quickly. So if this side drops by 6 volts, this side drops by 6 volts. If this side has dropped by 6 volts, this side must drop by 6 volts. This point is 0, this point is minus 6. That means that the voltage across the resistor is minus 6 volts. From here to here, we go minus 6 volts. This point here is below this point here. So this will drop down to minus 6 volts, which is what V was. So it drops down like that. Now, this side of the capacitor is at minus 6 volts. This side of the resistor is at 0 volts. That means a current's going to flow that way through the resistor, charging this point of the capacitor back up towards 0 volts. So the bottom of the capacitor is going to start charging upwards. The voltage is going to start increasing up towards 0 volts. So here goes upwards like that. When it's at 0 volts, that's at 0 volts, that's at 0 volts, that's at 0 volts there. No current flows there. Capacitor doesn't charge or discharge. So the voltage across the capacitor does this. Now that plus that must equal the must equal 0 essentially, because that's the supply voltage is 0, and the voltage across the capacitor plus the voltage across the resistor must equal 0. So if you think about that being there, then we add that shape to that shape, we get 0. Okay, but we're not done yet, I'm afraid. Then what's going to happen is this point's at 0 volts, this point's at 0 volts, and this point suddenly jumps from 0 volts, so this is charged now to 0 volts, this point suddenly jumps from 0 volts back up to 6 volts again. But the voltage across the capacitor cannot change instantly. It was at 0, there was no voltage across the capacitor. It's got to stay at 0, no voltage across the capacitor, which means that if this jumps up to 6 volts here, this also has to jump up to 6 volts here. So this point jumps up to 6 volts as well. So this point here jumps up to 6 volts. Now we have 6 volts here, 6 volts here, we have 0 volts here, so current is going to flow this way now. I'm just going to take charge off this side of the capacitor, reducing this voltage back down. So this has jumped up to 6 volts, and then it's going to discharge back down to 0 volts. So this will then discharge down. Oops, it does not cross the line. Okay. What's going on at VC? Well, VC is charging up like so. The potential difference is going up like that. Now, if you add that potential and that potential together, you get 6 volts. So the voltage across the capacitor plus the voltage across the resistor has to equal the supply voltage, and the supply voltage there is at 6 volts. Sorry, can't quite see that. So when we add that potential there, the voltage across the capacitor, that potential there, the voltage across the resistor, we always get 6. Here we got 6 and 0, here we got 0 and 6, and all of the things in between. So as this one drops down, that one goes up, like so. And the shape repeats. That's why it starts at 0 here. So the shape repeats by doing that. Okay, now that, if you haven't seen it before, is something that would be very hard to figure out in the middle of an exam. So hopefully when you did this capacitor charging and discharging experiment, you saw that on the oscilloscope. If not, and you got this paper, I think very, very few people will be able to figure that out from scratch. Can't do this one unless you get this one, really. So state and explain what changes, if any, you need to do to fit that on the screen. So before, the screen contained about that much. Now the graph is twice as tall, and on the old settings that would go off the top of the graph. So the first thing we need to do is we need to change the Y gain to half its value. So half the Y gain to shrink the wave vertically to fit the screen. Now the second thing is this starts at 0 here. 0 here is only in the middle of this. So what we need to do is we need to shift the 0 point upwards. So shift the 0 volts upwards to the middle of the screen. using the Y shift dial. Okay, so we need to shrink it to make it fit and move the middle up so it's in the middle of the box. Okay, tough question.